So good morning, everyone. So we discussed today about. Can you hear me well? It's okay.
It's a bit.
Wait. In that case, maybe the setting audio. Oh, how about now? Is it better?
Yeah, it's better.
Yeah, it's better, definitely.
So today we'll discuss about Markov chain. So I posted there in the Moodle Lantera. You can probably check. Okay. Ooh. Okay. So let's go to Markov chain. Share screen. Markov chain. Okay. Here it is. So, okay. So this is like the introduction. I have, I think, 5 slides there, right? So that means this week and next week. Okay. So so far what we have learned in OR has been deterministic, isn't it? Right. So everything is like in decision theory, we have some kind of probability, but still computing as deterministic. Yeah, the way we compute is always deterministic. So this time we try to do what is called stochastic process. Okay? So what is stochastic process? Okay. So basically, stochastic process is about dynamic of random state. Okay, so random process. Okay, or stochastic process is a family of model on dynamic random state. What is the meaning of dynamic? Dynamic means time dependent. Okay, so the time can be discrete, can be continuous. So t plus 1 plus 2 plus 3 or plus delta t, it is continuous. Yeah, and random, what? Random mean having some kind of there's an element of luck. Yeah, so relating to or having, okay, or being element or event with definite probability of occurrence. Yeah? There is some kind of luck or probability on the occurrence. And then when we said states, so yesterday we talked about it, right? It's an internal properties of the system that together with the input of the system will reveal the output. Yeah? So the state can be discrete or continuous, and the states are represented by random variable. Okay. The number of states itself are discrete. So now, stochastic process describe the time dependent of state in the system. So this is an example of random walk. Okay, and the actual x as a random function, yeah, that represent the trajectory of the states over time. Okay. Now, when we said realization of random variable, okay, the realization is small, like this. And this is the realization of the random variable x. It's a random function that produce different result. That means, look, I have a random function here, okay, and then each of these function will create one realization. So every time I generate, say, if I use F9 in Excel, okay, I will generate a new one, right? So it's random trajectory. Okay, so this is called realization. So can be up, can be down, and so on. So all of these are actually one function. In deterministic, one function means one line, right? But in stochastic process, it's not necessarily one line. It can be many lines, something like this. So we can describe stochastic process as a simple experiment. Okay? with a finite number of possible outcomes. So that outcomes is called states, which take place in stages. Okay, so look at the difference. This is states and stages. Okay. For example, okay, say you toss a die, okay, and then if the outcome is a certain number, for example 4 and 6, then you toss the first coin. But if the outcome of the coin is head, then you toss the second coin. But if the outcome is a tail, then you toss die again, and so on. So you see there are the outcome of one state, okay, one state depends on the outcome of the previous state, right? So the probability for each possible outcome at particular stage is known. Okay. Now, when the outcome of the previous stages are all known, then you can determine the next stage. Now, in Markov chain, okay, these states here represent time. Okay, these states here represent time, and the state here represent the node. Okay, the state with T represent the node. Yeah? The stages represent the time. Okay, so this is very general stochastic process. Okay. Say if you want to think of stochastic process, think about infinite sequence. So for example, you have x1, x2, yeah, xk, and so on. Okay, so the value of this is the states, right? So this is like the circle, yeah? The node. Now the value of the node can be varies. Yeah? For example, x0 is I0, x1 is I1, and so on. Okay, and then xk is I, and then xk plus 1 is j. This is the example. Yeah? So what is this I0 until I and j? Okay, these are all possible states. Okay, so let me give an example so that this become clearer. Yeah? Using symbol only is confusing, right? So say I have how many? 4 possible states. Yeah? M is the 4 possible states. So this is the realization of the weather. Yeah? So the weather in the K day. Yeah? So one realization is this. You know, x1 is sunny, yeah? x2 is windy, x3 is cloudy, x4 is sunny, x5 is rainy, and so on. So these are random. Okay. But these are just one realization. When I said realization can be when you run differently, okay, it will generate differently. Is it clear or not? The previous example here, is it clear? So this is basically a sequence, and then each sequence will have certain values. Okay. Now, when we said Markov process, okay, so consider that sequence of experiment which outcome depends only on the outcome of preceding experiment. So first order difference equation. Yeah, that is Markov process. Okay. So now application, right? You always ask, yeah? Leafy and Joy usually always ask, what is the application of this, right? So everything that you can put into state, discrete state, then you can put into Markov. Okay, example, in the stock, yeah, every tick, every second, yeah, or every tick, every buy and sell, right? The price can go up, go down, or unchanged, right? So you see there are 3 different states which is discrete. So then yes, you can use Markov chain. Say a mouse in the maze, and its intersection can turn left, turn right, go straight, or return back. So for example, that 4 state or 3 states, yeah, in the maze of the mouse, then yes, you can put as Markov chain. Similarly, migration, for example, how many people, yeah, population migrated from rural to urban to outskirt and to city center. Okay. These are examples that you can also use Markov chain. So in blood pressure, for example, daily, yeah, today is low blood pressure, tomorrow is high, maybe the next day is normal. Okay. So these are examples that you can put into Markov process. Again, also social migration. Yeah? Look, the time here is 1 generation instead of seconds or minutes. Yeah? So example here is percentage of women enter the labor force if the mother is also working. Okay? So there are 2 states, work or not work. Right? So that means the stage, the time. Okay? The stage is current generation and then next generation. So that generation can be 10 years, 20 years, okay, 30 years, that you define 1 generation. Okay, up to here, is it clear or not? So you know how to apply, right? So at least everything that you can put into discrete state, okay, then yes, you can put that into Markov. Yeah? So now terminology first. Yeah, the outcome of the experiment. So I put quote, yeah, experiment. Yeah? This is practically numerical experiment, right? So the outcome of that experiment is called state of the process. Okay, at its regular time interval, the process will jump, yeah, to the different states, different possible states, and then that which state to go. Okay, which state to go in the next time, you define the rule. Okay, that rule, okay, from one state to the next state, okay, you can describe it into a tree or a matrix table or a diagram. Yeah, so this is called transition diagram. Example, this is the matrix. Okay, so you see here, this is current. The row represents the current today. And then the column represents tomorrow. Yeah. So in this example, we have 3 states, 1, 2, 3, or A, B, C, right? So that means today, for example, this is state 1, yeah, row 1 in here, right? If today is 1, okay, and tomorrow we have a probability of 0.5 to be in the same state 1. We have probability of 30% to be in state 2, and we have probability of 20% to be in stage 3 tomorrow. Okay, so this matrix can also be represented as finite state diagram like this. So this is transition graph. Or if you want to make it more complex, so we can also make it into tree. Yeah? So today, this is tomorrow. Okay? And this is the probability. So up to here, is it clear or not? Easy, right? Oh, very easy, yeah. Markov chain, very easy, yeah. Okay, wait until later. Okay. So the purpose of Markov chain is to capture the probabilistic behavior as a function of time. Okay. Remember the node here. I put the node here. Eh? How many nodes? Yeah, this is 1, 2, 3. This is the node, and these are the links, right? These blue are the links. So for each of these, you see, for each arrow going out of one state, so you see 0.5, 0.2, and then 0.3. Oh, the probability is, the sum of probability is 1. Yeah? Going out, you see, 0.5 plus 0.2 plus 0.3. The same thing here, 0.1, 0.9. So the sum is 1. Okay, the same here, 0.2, 0.2, and then this must be 0.6. Right. So that means in the matrix, the sum of this per row is 1. Clear? So this is called stochastic matrix. Why? Stochastic matrix is a matrix where the sum is 1 for each row. Okay? Just a minute. Okay, so the node represents the state of the system. Yeah? The time is discrete. Every minute, every stage, every hour, every day. It's up to you, yeah, to define what is the discrete time in here. Now, each state has the set of rule, right? That rule is based on probability, okay, to go to the other state for one time step only. Yeah? And that rule represented by link. Okay, so of course the sum of probability to go to the next stage, the sum is 1. Clear, yeah? Super easy, right? Okay, so this is example. Okay, so you have how many states here? You have 2 states, yeah? State 0 and state 1. And the name of the state is up to you. Yeah? So here from 0 to 1, okay, the probability is P, right? But remember the total out is 1, so that this one must be 1 minus P, right? The same thing here. In state 1, okay, if this is Q, that means this is 1 minus Q. Yeah? Okay, yeah? Clear, yeah? So the states are labeled by 0, 1, 2, 3 or ABC is up to you. Okay? Now every time slot, okay, there is a jump decision, random, based on what is the current state. Okay? So, and the sum of probability to all columns must be 1. Okay, so sometimes the arrow back to the itself is omitted, yeah, so that simplify the drawing. But you need to know that the sum of probability is 1. Okay, random walk. You know what is random walk, right? So say this is the current state, okay, a drunkard, okay. There is a probability that go to the right or go to the left with certain probability P. Okay, at each time step, we go to the left or to go to the right. Yeah, so with certain probability. Yeah? So you see, we can put it into this equation. Very simple, right? So xt plus 1, yeah, to the right, or xt minus 1. Yeah? This is the depends on the problem. And you see the function is actually a decision, yeah, decision function. So there is a 2 if then, yeah? If the probability is P or 1 minus P. Okay. Oh, queuing. Last time we talked about queuing, right? So queuing is also single solver queuing, yeah, is also basically Markov chain, right? So in supermarket, for example, at each time slot, okay, the customer will arrive, yeah, will probability T. Yeah? So it's up to you to decide the probability distribution here. So last time we used Poisson, right? Okay. And then at each time step, also customer will leave with certain probability Q. Okay. With this, now you can actually derive any kind of probability distribution. Yeah? Last time we always use Poisson and exponential, remember? Okay. At this time you generalize it. Okay. Oh, what if I don't use Poisson? How if I use Bernoulli, for example? How if I use geometric? You can. Okay. Because now you are having much more powerful tool, which is called Markov chain. Yeah? The same, right? Last time we already derived it, but Markov chain is a tool to derive all this formula that you have in the queuing theory last time. Okay. I don't do derivation in our class, so, but if you want, okay, there are many books I can supply for you if you want it. Okay. So, okay, come back. So this is called transition probability. So I call this stochastic matrix. Why? Because the sum of each row is 1. Okay. And the entries, because these are probabilities, so the entry is between 0 to positive. Yeah? Cannot be negative. Yeah? And must be less than or equal to 1. Right? because the sum of the entry is 1. So the total probability, each of these, if this is not 0, that means there is a link. Okay? If 0, there is no link. Okay? So now the total probability of all link out of one state is 1. Yeah? So of course this is a square matrix depending on the state of your Markov chain. Yeah? So say you have n state, and then what is the meaning of this? Okay? This is the probability to go to the next state given now you are in the current state. You're familiar with conditional probability, right? Bayes rule, conditional probability, no problem with that. Okay. Okay. Anytime you feel confused, you tell me so that we can review the background knowledge. Okay. So okay. Anyway, so Markov chain as stochastic. So in Markov chain, yeah, the stages are called time. Okay. If the stages is space instead of time, yes, possible, right? Okay. So then you, instead of having Markov chain, there is another name. Okay. That name is MRF, yeah, Markov random field. So exactly the same like Markov chain, but that is instead of time, now you use space, okay, in the lattice, for example. So totally different things that we don't touch in our class, but if you want, you can start to search, yeah, in Google. Okay, there are many books, and if you need, I can supply you again. The possible outcomes are called state, okay, with T, state, not states. So the possible outcome probably the head, the tail, 1 in 6 of the die, and so on. This are called state. Okay. Now, the variable to locate where we are in the experiment is called random variable. Okay, so state, and random variable. I hope you can understand the informal definition here. Okay, so the Markov chain can be considered as a sequence, okay? A sequence of random variable, okay, which correspond to the state of the system. Yeah? So I'm calling this as trajectory. Yeah? The sequence is basically the sequence of node, right? So basically the trajectory. Yeah. So one realization of that random variable is the infinite sequence. Okay. So this is the trajectory. Now, if the value of xk, so k is the value of state xk, okay, is given, then the value of xk plus 1 is independent of, from the beginning until xk minus 1 is not, you ignore that. Okay? So only the value of xk plus 1 only depends on the value of xk, not depends on the previous value. You got this or not? This is the main assumption of Markov. That is what definition of Markov. It's just first order. Okay. Later on, of course, if you want to generalize to second order and order, that's fine. But the real definition of Markov is it depends on the previous only. Okay. This is called Markov property. Okay. If the value of xk, look at this, k is the time, yeah? If the value of xk is given, then the value of xk plus 1 is independent of previous value. Okay. Even from 1 up to k minus 1, you forget about this. Okay. So we put this into probability. Look at the notation here. Okay. I put the probability of xk plus 1 equal j, okay, and then you have a sequence, right? Sequence starting from x0, x1, and so on until xk, right? So given that you already passed all this sequence, what is the probability to go to the next stage with this j? Now you are in I. Okay. That probability, okay, you can forget all this previous one because this probability is exactly the same as this probability. Okay, which is just xk minus k equal I, and then k plus 1 equal j. So this is one-step transition probability. So that's why we call this more memoryless process. Yeah? It does not remember the past. I can delete all this. Is it okay or not? That is the assumption of Markov. Okay, so if you are in current state is I, okay, the probability of the next state J is this one, right? Okay, so Markov process or Markov principle is independent of the future from the past if the present is known. So the future depends on today, not in the past. That's the easier way to interpret Markov. Okay, so the experiment are run on daily basis. Okay, and if you say it's Markov process, that means okay, the probability of the outcome tomorrow depends on the outcome today and do not depends on the outcome of any past experiment. Then this is very strong assumption, you know, because you can delete all this previous value in the back. So because this is stochastic process, I give a notation S. Okay, this probability in my slide I put notation Sij. Look at this. Okay, Sij is today in I, okay, tomorrow in J. Can you see the notation that I'm using? Okay, K is the time, K plus 1 is the time. Yeah. K plus 1 means tomorrow, K is today. So today you are in I, tomorrow you are in J. So I put it as Sij. Okay. Now, stochastic process with finite number of states. So the number of states is finite. Okay, so limited, not infinite. Okay, because if infinite, we have infinite Markov chain, but the result will be totally different. The probability of being in particular state, okay, depends only on the state occupied at that step. Okay, that dependency also the same for all steps. That means the stochastic matrix a while ago, the transition probability matrix is also not depends on time. Okay, the transition probability matrix is not depend on time. That is constant. That's the main assumption in here. Oh, when you ask, can I make it depend on time? Yes, you can. Okay, but we don't discuss in our class. Okay? You can. In reality, yes, you can. Okay? Say for your research, for your thesis, you can use that, or for your project. Yeah. But not in the lecture. So this is the definition of Markov chain. Yeah? Okay, so an experiment with the finite number of possible outcomes, okay, repeated number of times. Okay, the sequence of the outcome of the Markov chain is n square number Sij, so that the conditional probability, this one, okay, of the outcome is given by this value. Okay, so that is just the formal definition. I already explained everything, right? Okay, then if I put that, okay, you can see now I put S here is the transition matrix. Okay, you have states x1 until xn, okay, and then these are the element of the stochastic matrix, yeah, or the transition matrix. Clear or not? Just definition, yeah. Now, this is an example. Okay. a small town has only two supermarkets, A and B. Okay, the marketing research indicate that the next shopping day, okay, a number of customers will switch from A to B with probability alpha, and then from supermarket B to A with probability beta. Oh, can you create the transition matrix of this problem? Oh, you can annotate here if you want. How many states? What is the state in here, in this case? I cannot hear you, Livy, if you're talking.
Two.
Okay. What is the state? What are the states?
Two supermarket.
Correct. A and B, right? Very good. So can you make the transition matrix?
Do you want us to annotate?
Yeah, you can annotate here. So S equal, so I have A and B, right? And I have A and B, right? Okay. So what do you feel here? Which one is A alpha?
Switch from
So switch from A to B with probability alpha. Where you will put alpha?
so A comma B here.
Yeah, okay.
Wait, this one.
So it's going that direction, yeah?
Here.
Yeah, so here is alpha, right? So, and then, which one is beta? Where is beta?
Beta is in the opposite one. The left, yeah.
Yeah, so here is beta, right? Okay, but remember the sum is 1. Okay, must be 1, right?
Mm.
So that means 1 minus alpha. This is 1 minus beta. You see? Okay, you can make it, right? Okay? Okay, let's go. Oh, wait, I will, how to remove that? Okay, sorry. Come back here. Yeah, so there, okay, we have that, okay. Oh, do you want to practice this? If yes, I will give you the stock data of PCA, or you can find. This is the bank of PCA. So, or you want to practice this in as assignment? Maybe I'll give you the data later in Lentera. I forgot to put this in Lentera. Markov chain. Okay, so the point is this. Okay, if you have a price data, okay, if you have price data, so then what you will do is you calculate what is called return. Oh, there. Okay, so can you see my data? So this is the data. Okay, this is the one that I will give you later. Okay, this is the data from 2004 up to 2020, okay, July. Okay, so, and then what you will do is to create Markov chain based on this real world data, right? So how are you going to do that? Any idea first before we discuss? So you have a real world data, yeah? This is the data is high, low, open, close, and the volume adjusted close. Okay, this data from the internet, right? Then the question is, how are we going to create a Markov chain of this? Oh, Liffy, any idea? Or Joy? Think first. What is the Markov chain? Right? If you want to apply something, right, you need to you need to know the definition, right? Oh, I need to create a sequence, right? Sequence in here you have data of daily sequence, so that means you have the data of daily sequence, but you need to put it into discrete states, isn't it? So you need to discretize this. So what is the state that you can think of? Okay. So states mean change, isn't it? Daily change, correct? So in that case, how if the first what I will do, okay, this is my suggestion only, so you can do different things, right? So my suggestion is I calculate what is called OHLC price. Yeah, what is that? Open, close, low, high. I average all of this. The 4 price here. Okay, I take average. So here, yeah, the average of this. Can you see? Okay, so this is the average of the previous sheet. Okay, and then I just copy down, right? Okay, so once I know the average of the price, so I have single price. Okay, this is the daily average. And then what I will do, I will get the return. Okay? What is return? Okay, I put in the slide there. Okay, share screen. So can you see? So the return is the return of today, okay, equal to the price today minus the price yesterday divided by, oh, sorry, this must be supposed to be minus 1. Yesterday, should be yesterday, not today. Okay, so this one supposed to be divided by yesterday, that's correct. Okay, today minus yesterday divided by yesterday. Okay, so once you know the return of the price, right? So what you will do, you just put a threshold. Yeah? So you just put a threshold that you define on your own. Yeah, this is yellow, so you can define the threshold. Okay, so if the value of the return is below certain threshold, I will call this D, down. Right? If the value of the return is above certain threshold, I will say up. That means the price is up. Okay, the price is down, the price is up, or the price is actually still the same, stay in the same range. Clear, yeah? Okay, so you can discretize, okay? So, and then how do you get the transition? Up to here, is it clear or not? Clear, right? You,
I want to ask about the thresholds.
yeah, I will discuss the threshold
Okay.
later. Okay, so first we talk about transition first. Okay, how do you get the transition? Oh, very easy, yeah? Because transition I mean the two state, right? So then you just combine, yeah? I just concatenate here. Can you see it? Okay, so and then you ask, okay, how I determine the threshold? That's Joy asking, yeah? Very good question, yeah? So yes, it's up to you actually to decide the threshold. What I'm doing here is to create the statistic. Yeah? So I have total, the count of the return is 4,007 data, right? This is the maximum, this is the minimum. Remember, return is can be positive, can be negative, right? So, and then the range means the maximum minus the minimum. Okay, this is the mean and the median. And then I get the percentile. Okay, I get the percentile. So one way to decide the threshold is to use that percentile, right? So I use this percentile. Basically, this is just copy of the 1/3 percentile and 2/3 percentile. Right? So if you don't like it, you can change the percentile. Yeah? You can change. For example, instead of 1/3, you can say, oh, I want just 30%. So then the threshold changes, right? So here I put 1/3. Okay, so 1/3. Right? So still 20%. Yeah? Okay, now if you look at the distribution, oh, this is interesting. Yeah? Now I create a bin, and then I created the frequency of this return, right? And look, the distribution is look like normal distribution actually. Right? Not distribution of the price, the distribution of the return. Right? Close to normal distribution. Yeah? In fact, this is log normal actually. Okay, it's well known that any stock, okay, the distribution usually log normal. Okay, so based on that, so I can just get the transition, right? From here, I just count, yeah? In Excel, I just use count if. Right? Count if, okay? Now I have a concatenate of D, D, DS, DU, and so on. So then I just use count if here. Can you see that? Can you see the formula here? Okay, so this is just the count if of the transition matrix, the transition column, okay? And then concatenate of this symbol, yeah? D means down, S means stay, U means up, isn't it? Okay, and then, okay, I got the flow. This is basically the flow, okay? So what I will do, I will get the outflow probability, right? Transition matrix of the Markov chain is basically outflow probability. You see, easy how to get. That means that value divided by the sum on the right side. Yeah? Okay, so of course with that you can get all 100%. Okay, you get the transition matrix, you get the Markov chain.
Sir, I want to ask, how would you, since I'm not familiar with stocks, how would you interpret like the metrics? Like how would it be useful for like the traders?
So you can basically think it this way. There are many ways to model stock market. Okay, this is just one way, and this is not even accurate, but that depends on your threshold actually, right? So you are right that the threshold matter. Okay, so because of this threshold, you will see this is actually pre-magic. You see, because I put 33%, 1/3. So you will see exactly this one. The sum of row and the column is exactly the same. Yeah. So this is this is later what I call as ideal flow, is something like this. Yeah? That the sum of columns, you see 1, 3, 3, 6, 1, 2, 3, 6, 1, 3, 3, 5, and so on. So one way to interpret is, look, I have this transition matrix, okay? Then I can generate the next value, right? If I know today is what value, I will know what is the, I can predict tomorrow, I can predict the next day, and even more than tomorrow. Okay, so if this is not correct, what you will do, you will change the parameter. What is the parameter? This is the in yellow. Okay, so you try to calibrate. Okay, probably this is the one that is not correct. Yeah? Over time, you can generate new transition matrix based on your realization. Okay? Because the realization is the one that based on the real world data. Okay? So basically, if you can create the real, the correct one, the correct transition matrix, you probably will have a very close prediction to the real world. Okay, so this is the nice things about this. Okay. Do I answer your question or? Okay, so remember like this. Any stochastic process, yeah, not just this Markov chain, yeah, any stochastic process will have a fundamental understanding like this. Look at this. Any situation that I want to model have certain underlying phenomena behind. Okay, there is certain underlying phenomena behind that I don't know, but I probably can capture that fundamental phenomena behind, okay, through certain kind of distribution, certain kind of model. Okay, so in this example, I capture that, for example, using return distribution. Okay. In this example, I capture that fundamental things using Markov chain. Okay. So given if that my assumption is correct, this is very, very big things. So if my assumption is correct, that is actually exactly match or close to the actual model of the real world phenomena or the nature, then I can predict correctly. Okay. You are the modern wizard, right? In the old days, yeah, you have wizard, right? Yeah, the magician, right? In the past, the magician will do prediction based on what? Based on mystic, yeah? Based on magic, yeah? Based on trick, right? So modern wizard, you are the modern wizard. What you will use? You will use statistics, right? You will use mathematics, right? So you will use science, yeah? Okay? But the job is still the same, you know. Okay? The job is still the same. It is to predict something, right? To control something. Okay? Don't forget, you are modern wizard. Okay? You are the magician of the world. Okay? So your job is to predict. Then you will ask, how can I predict? Okay? You predict based on assumption. The assumption is your model match with the real phenomena, real world phenomena that is behind the scene. So if you can capture that and that is correct, then of course all the science is correct. But if that does not really match, then maybe you will try another model. Right? That is the way to do. So that's why we study a lot of different models, okay? Because we don't know which one is match with the real world phenomena. Okay. So finding the match model, the correct model, is an art, it's not science. Okay. The science itself is start from the assumption, creating the model, okay, giving all these properties of that model. So what do you think? So with this, you practically use Markov chain for any data, right? Do you have more confidence with the Markov chain now? Okay. Okay, let's come back here. So this is an example. Can you see my slide? Right. So you can get the threshold based on the percentage of the return. Yeah. So in this example, I give 33% and 67, 67%. Yeah. So, but it's up to you to decide. Okay. The threshold. Okay, so this we already show a while ago. Okay, oh, I already show also in here. Okay, so let's go to the detail on how are you going to predict, right? Okay, so I use notation pi here to show that this is the node probability. Okay, so I said state probability at time k. Okay, this is the laser. Okay, so this is the k, meaning vi. Okay, instead of very long notation like this, okay, PR probability of xk equal 1 equal I will shorten it, okay, into vi. Okay, so what is this? This is the state probability at time k. Okay, so how about probability at time k plus 1? Okay, is j, right? So then I will put as j. Yeah. So now the transition probability a while ago, yeah, the stochastic matrix a while ago, yeah, is I will put as Sij, right? So that means currently at I, tomorrow at j. Yeah. So this is a review of what is the meaning of conditional probability. I hope you remember. Okay. So a probability of a random variable A given another random variable B, okay, we symbolize as this, yeah, P A given B. Yeah? So what is the definition? The definition is this is the joint probability, yeah? A intersect B. Yeah? So I put comma here instead of intersect. That's the same meaning. And then divided by B. You look at this. This is the divide by B. So I will put here also divide by B. Okay. And then if I multiply this one and this one, I will get that one, right? So this is exactly at the bottom here. Okay. So if I have a joint probability, okay, I can always put out. So I can put like this divide, and then the bottom one I put there. So this is called multiplication rule. Okay. So conditional probability A given B should be read as the probability A will happen, okay, given that B already has, okay, or the probability to select A among B. Okay, don't forget, yeah, B is given first. Okay, then we find the proportion of A among B. Okay, so now you know this Sij here is basically transition probability with this conditional probability. Yeah? So, okay, now if I have this, okay, as this is the transition probability, can you find the probability of x3 A, x1 is B? How do you calculate that? Any idea? today you are in state B. Say in your stock a while ago is normal or state. Okay. A is probably up. What is the probability that 2 days from now, okay, this will go up, the stock will go up? You want to know that probability, isn't it? Okay. Smell money, so that's probably more interesting. AB is not interesting, right? But when I said this is your stock, okay, will go up. Oh, what's the probability that the stock will go up? Oh, now that's smell money. Okay, so how do you get that, right? This is prediction, isn't it? So I just throw this stochastic matrix into the finite state diagram. Okay, so to get that, okay, you need to use what is called total probability, right? So look, today you are in B. Yeah, you see, today you are in B. Right? Today, tomorrow you don't know. Yeah? Tomorrow can be B, A, or C, right? And then the next day you want to know what is the next day is in A. In that case, you find all the path, right? What is the probability of this path plus probability of this path plus probability of that path, isn't it? So that's exactly what we are doing here. Yeah? This is called total probability. So you see, so the probability that x3 is A, given that today is in B, okay, that is equal to probability of tomorrow is in A, this one, given that today is in B, multiply by, okay, what? The next day, which is the day after tomorrow is in A, okay, that tomorrow is in A. This is the path. Yeah? This is the path probability of this one. Is it clear or not? Okay, plus, right? Because these are all possible paths, so you go to the next part, which is this one. What is this? This is the tomorrow is B, today is B, multiply by the next day is A, previously B, right? So here, yeah. Today is B, tomorrow is B again, and then from B to A. Yeah, and then what is this part? This is B to C, C to A. Yeah? So you look at this, B to C, and then C to A. Okay, so in this small notation is easier. Yeah? This is like very long, right? That's why I simplify the notation so that you can see. Yeah? So this is like A, B, so that one is, when you read this, you need to put from the last to the front. Yeah? So this is like BA and then AA, right? This one is BB and then BA. Yeah? Can you see? And then this one is BC and then CA. Yeah? So here. After that, it's easy. Yeah? You just plug in the numbers, you get the value. Up to here, is it clear or not? So you can predict, okay, given the Markov chain that you have, the transition probability that you have, now you can predict 2 steps, not just 1 step. Yeah? You can predict 2 steps. 3 steps, you can also do the same thing, right? So you just find the path, all possible paths. Is it clear? Any question up to here? So you know from the data, you can create the Markov chain, which is the transition probability. Right? And then from here, you can already predict. That's how you apply, right? And then, okay, let's do this. Okay, practice. Oh, this is an example. Okay. So I have a new one. Okay. Suppose this is your transition probability matrix. This is your Markov chain. Okay. Now I'm giving you the initial state. Yeah. VA, yeah, at time 1 is A is 0.3. Okay. VB, okay, x1 equal B is 25. And then VC, okay, x1 is equal C is 45. So now I want you to calculate the path probability. A while ago I calculated all the path, right? So this time I will ask you to calculate only one path, which is B to C to A. Oh. Can you calculate that? You can calculate on paper and then or in notepad and then share your screen. Okay, I will stop sharing so you share your screen. Oh, okay. So we have B, C, A, right? And then
So we start with P, right? So it's 0.5. Then from P, we transition to C, it's 0.5. And from C, we transition to A, it's 0.35. Then the probability is just multiplied.
correct. And then you need to multiply with the earlier. Okay. So yeah, very good. Yeah, the result is correct. Okay. So the one that I want you to understand here is the actual Markov property that being used here. Okay. Shall I share my screen? Okay. Here it is. Can you see my slide? Okay, so if you look at this, you have what we want to find is actual joint probability of three things, correct? Okay, three things, no? That x1 is B, x2 is C, and then x3 is A, right? And then to calculate this, okay, you're supposed to calculate one by one, yeah? all of this. So let's do it one by one, okay? So you have say x1 is B, x2 is C, right? So if you have this joint probability, what you will do, okay? So you divide this, right? So then you will say, okay, I have x1 is B earlier. Given that x1 is B, what is the probability that it will go to C in x2? Okay, and then of course, because this is joint, so you can use the multiplication rule, right? You have this value. Okay, with this x1 is B, given the x1 is B, what is the probability of x2 is C multiplied by x1 is B? So I can put this is what is this? This is actually SBC, right? And then x1 is B is 5 phi B, yeah? 5B. Okay, and then how about the three of them? If you have the three of them, okay, now I will say, okay, I can put up like this, right? That the day after tomorrow is in A, given that, okay, today is in B and tomorrow is in C. So if you look at this, okay, this must be divided by this joint probability, right? With this x1, x2. Can you see this or not? This is the actual things that you need to calculate. Okay, you're supposed to have this. Okay. However, look at this. I can calculate this later, yeah. This one I can calculate. This is just divided by that, right? But this is the one that difficult, you see. Yeah? This is the one that difficult to calculate, right? So this is the one that you actually simplify. Okay? So you see here how I simplify. Instead of getting all the way from x1 up to xn, okay, minus 1, yeah? So here I will just put, I forget everything. Yeah? I just get the last one. So you see, yeah, x3a1 until x2. Yeah? That means I only get the last one. This is the Markov property, right? Remember the definition earlier. What is the meaning of Markov property? I forget everything else. I just remember the last one. Okay, that is the one that very strong assumption here that we put. Okay, so using this, you can see now I can just put this, right? So this one I put here, okay, and then this one I can just separate. Yeah? This is exactly this one, so I just put exactly this. So I put it here. That's why you get this result that you calculated. Yeah, that Joy that's calculated. Yeah. So if you said B, C, A, then phi B, okay, and then BC, and then CA. Yeah? S, BC, and then SCA. Is it clear or not? So why I get this formula is because I make an assumption behind this with this Markov property. Without this assumption, you still need to calculate this very long part. Okay? Okay, so how about this? This is exactly the same as earlier. Okay? But the difference is this. Given that x1 is already given, is P. Okay. What is the probability that x2 will be C and the x3 will be A? What's the difference? The difference is now I keep that x1 is already p. Okay, so because I already, okay, the formula earlier, the formula a while ago, we can still use the same thing. Okay, the only difference is because this is given, right? That means the phi b is known with is 1. Okay? Why? Because surely you are already there in b, right? So if you don't trust this, okay, I give the way to compute another way. Yeah? So I'm just deriving this computation using conditional probability. Yeah? So you see that this one equal to what? The join divided by phi b, right? In that case, I can calculate everything. So you see phi b divided by phi b, no more, right? So you get exactly the same result. Okay. Practice this now. Exactly the same thing. Okay. But now I'm telling, it's known that the process will start with initial state x1 equal b. Livy, try. Hey, don't forget to claim your recitation point, okay? Every time you recite. So, what's the difference with earlier?
With the previous
Yes,
question,
the previous two.
the previous two.
Hmm. So look at the notation, okay? The, earlier I'm using given like this, right? And then the first one that Joy was practicing, I used the joint probability, right? Now I'm using the same exactly, okay? I'm using exactly the same joint probability, okay? But I'm just telling, it's known that the process starts with x1 is b.
So then we don't need to use the, like before we use the 0.25, right? So now since
We
it's
just use
fixed,
one.
one, yeah.
Yeah. So that's exactly the same as previous example. Okay? So the only difference is now phi b now become 1. So exactly the same as previous example. Okay. So of course you know, right? So if you know you are in state B, that means the probability of that state is 1. Okay. Remember that. Why? Because it's already sure event. Right? It's known already, so that means you already sure. There is no need probability because that's already sure. The probability is surely 1. Okay, huh? Okay, so this is exactly the same. I think. What's the difference? Oh, the part different. The part is different. The part is not the same. So this is A, B, and C. So if you look at this, Yeah, from A to B is this one, 0.2. And then from B to C is 0. Right? That means, of course, the probability is 0. Okay. The computation is still the same, the formula is still the same. When you plug in, you know that B to C is 0, so everything becomes 0. Okay? Just to make sure. If you look at the computation, very easy. Yeah? Okay. If you want to know the path probability, the first one, you put it as VA. Yeah? This one, because the first one is A, right? So you put it as VA. And then the next one is this one. 1 to 2 is AB, so AB. Yeah? And then 2 to 3 is BC, so this one also BC. Okay? Easier to compute with this. Okay? But probability is always like this. Yeah? So the initial one is the initial where you locate it. Yeah? And then after that you just follow using S. Easy or not? Yeah? Using this notation is actually easier than using probability notation like this, very long. Okay. Oh, can you calculate the condition? The first one, Leafy, the second one, Joy. Okay. Okay. The first one is Leafy, the second one, Joy. And then you share your screen.
Can you share your screen for a bit again?
Oh, okay.
Second one.
Yeah, the second one is Joy.
Okay.
The first one is Leafy. Put into the formula and then you plug in the value. Okay. Do you understand this practice is about? This is X1 is A, mean you are currently, right? And then you want to predict that tomorrow will be B, and then the next day will be B again. This is a prediction, basically.
The result is 0.12.
Very good, yeah. You want to share your screen, Vivi? How do you compute that?
Oh, I do it on my paper.
Oh, okay.
So for the first one is the probability of x2, x2b, and then the x3 is b. From the x1 is a. So we start from a. A to a is 1 multiplied by a to b. It's 0.2 multiplied by b to b, 0.6. So I got 0.12.
Okay, 1, 2. All right, 0.12. Yeah, very good. Joy?
I have the same result.
You get the same result. Yeah. So you see, even if you shift it, if you look at the two of them, okay. So even if you shift it, okay, as long as the sequence is the same, you get the same result. This is what is showing that Markov chain is actually memoryless. Right? If the sequence is the same, the time does not really matter. Right? Okay. So if you look at the value, okay, this is exactly the same, yeah? A, B, B, right? So A, B, B. The only difference is only the time, okay? This is 1, 2, 3, this is 2, 3, 4, right? So, yes, of course, the formula is the same, the value is the same. So there is no difference, right? So it's memoryless, okay? So now this is also the same thing, okay? If you know that the process start with initial state x1 equal p, then phi b is equal 1. Okay? So this is exactly what you're supposed to do. So again, in this practice, you can see if I know B and then A and then C, okay, what you will do, you just change this. First time is B, this is phi, okay, and then you go to the transition, yeah, from B to A, right, and then from A to C, okay. But because we know that phi B is already given, that surely there, then the phi B is equal to 1. So exactly the same thing. Okay, so this is already, we talked about this. Okay, so if you want to draw the transition graph from the transition matrix, okay, you look at this. Every zero you don't need to draw. Everything that above zero, that positive, that is the one that you draw as link. Okay. So from the finite state graph, you can also get the transition matrix, yeah? And then you can also from transition matrix to the transition graph. Okay. No problem, right? And don't forget, okay, the sum of all outflow here, okay, probability, okay, out probability is 1. Oh, now I have only 2 states. Can you draw the transition diagram? Can you draw the transition diagram? Yeah, you can draw on paper. Okay. Supposed to be simple also. Right? Only 2 states. Okay. So you're supposed to get something like this. Yeah, okay. So it's supposed to be this is S00, S01. Okay. So far, is it clear or you have any question? So you know you get from data, you can create the Markov chain, yeah? Which is just the S this one, or the diagram. It's the same thing, right? These are two are the same thing, okay? And then from there you can get back. Yeah? So from the diagram you can get back the matrix and so on. Okay. Okay. So if you have the states are say 1, 2, 3, I put number instead of ABC. Okay. Then the state probability at time k plus 1, yeah, given that today is in k equal I. Okay. So you can calculate this, right? Then you can sum, right? Sum of this part, right? This is the sum of the part. Okay. From here, we can derive the Markov chain formula. Yeah? So this is the Markov chain formula. Can you see? Okay. So the next, this is the node value. Okay. The node value of J in the next time equal to the S, the stochastic, multiplied by the V, yeah, at time k. And then you sum of all I. This is I mean the row, yeah? Sum of all rows. Okay. So if you look at this formula, what is this? This is actually difference equation, yeah, the one that you just talked about yesterday, right? Exactly, yeah. So this is first order discrete canonical system. Yeah? Okay, so now you can see the connection between the Markov chain and difference equation, yeah. Okay, okay, let's practice that. Okay, so I have two states, okay, of Markov process with say I have two states A and B, okay, and then the probability to go from A to A is alpha, right? Of course, A to B is 1 minus alpha, right? So B to A is beta, and then of course this one is 1 minus beta, right? So let's create the difference equation of this Markov process. Huh? So in that case, I will put AK. Yeah? AK is the probability of the process at stage A at step K. Yeah? This is at time K. Yeah? BK is the probability of the process at state B at time K. Okay, so let's define this two, and then let's create the difference equation of that. Yeah. So remember, this transition matrix means this is current, this is tomorrow. Yeah, this is today, this is tomorrow. Right. So you know the Markov chain formula. This is the one that I gave a while ago. So then we can just put in. Yeah, very easy. So that means AK, this one, right, plus 1, okay, mean equal to what? Alpha, this is Sij, right? And then times Vi, which is this one, right? And then remember we sum it at all rows, yeah? I equal 1 to n, yeah? I mean the row, right? So that means beta, okay, Sij again, multiplied by Vi, which is Bk. Okay, can you get this? Davy, can you get this or not? This first equation. Yeah, this comes from this MC formula. The same thing, yeah. So now you go to the next column, right? Each column is one equation. Yeah? So the next column you get again 1 minus alpha. What is that? Sij, right? Okay, and then multiply by AK, okay? And then plus, yeah, this is sum, right? 1 minus beta, this is the Sij again, times Vk, what is that? Pk. Okay, so the next question. Oh, now I have of course, AK plus BK, this is must be 1. So I have 3 equations. Okay. Clear? So if you have this stochastic matrix, yeah, or transition matrix, you can always create the difference equation. Okay. How? Yeah. Use the MC formula, yeah, the Markov chain formula. So I try to connect, okay, the difference equation with the Markov chain. Yeah. So up to here, is there any question? Is this too fast or too slow? Or just okay? Can you grasp it? Okay, so far okay, right? So now if you have that, okay, if that you have this earlier, right? So then we can compute, yeah? We can continue that, right? Remember, this is the one that I copy, yeah? I just copy here. Okay, I combine that now. AK plus 1 equal alpha K plus beta K. Yeah? This is, I just put in here again. Okay, so, but I also know that BK, right? BK is already here and is also 1 minus AK, right? So, and then I can put them together, okay? I can put them together into one equation, yeah? This is just algebra, right? So, oh, if you look at this, what is this? AK plus 1, okay, alpha minus beta times AK plus beta. Oh, now I have, what is this? This is affine difference equation, which you know already the solution, right? Right? Oh, if you put that the solution into it, okay, this is the solution, right? So what is that? If you look at the solution here, okay, you know that alpha must be alpha and beta must be between 0 and 1, right? And then alpha minus beta must be less than 1. So now if you look at this, because alpha minus beta is less than 1, and then you exponent to k, right? That means it will convert to 0, right? So this part will convert to 0, okay? That means AK in the long term will equal to this value. So look, I can get the long-term behavior of Markov chain. Wow, isn't that nice? Yeah. In fact, when you see the queuing theory that I gave you last time, okay, all of those are the steady state, I mean the long-term behavior. Okay. So how do you get the long-term behavior? You put it into dynamical system, okay, and then you get the limit of k to infinity. Yeah. Okay, this is just one example. My point here is, do you understand the meaning of steady state, long-term behavior? Okay. The computation you don't need to remember, but the meaning only. Okay. The long-term behavior means I want to get that Markov chain a while ago. Now I can get the AK and BK. Okay. So from here I can get also the BK. Right. So with that, if I know alpha and beta, right? So in the long run, it will go to state A with this probability and go to state B with this probability. Okay. What did you just get? What do you understand about this? We can calculate the long-term behavior of Markov chain. That is the one that we are interested in, actually. Okay. Of course, you can predict, if today, tomorrow, what is the stock market that you're thinking. That tomorrow what is the, yes, you can. But in Markov chain, you can go beyond that tomorrow, In the long term, what will be the probability? That is the one that we are interested in. Okay? Something more than that just tomorrow, right? So this is the ideal condition, in the long-term behavior, the steady state. What will be the probability? That is the one that we are interested in Markov chain. Okay? Is it clear or not? This is just the computation. I just copy that. Okay, the rest of his is just the simulation. So simulation, I will just skip this, okay? But I will just discuss a little bit so that if you want, you can practice. If not, you don't need. So given the Markov chain, okay, you can create a random number. See, this is the statistic, the transition matrix that you have. Okay, then you can move the token from state to state. Okay. That eventually you will be able to get back. Okay, how many times it will visit that state and so on. And these are the movement of the state. So if you want to do it, okay, I give the formulas in the slide that you can also do on your own. So I will show you the simulation in Excel. Can you see the Excel? Right? So this is the transition state that we can input, and then I have an initial state here. Right? And then I just create a random number. Okay, random number that every time you press F9, it will generate new one. Okay, from there I can get this transition matrix multiplied by the random number. Okay, and then from there I can get the maximum of that random number, Q times the random times transition matrix. Okay, and when that happens, say for example here is 0.49, the maximum, and then arcmax means which state it happened. Okay, so that state that happened is the one that I put it here. Okay, so initially 1, and then the next one I just put based on this. So if previously 1, okay, what will be the next state? Can you see? This is based on the index. Okay, and then from there we can get, okay, now you are in the state 1 and so on. Okay, and then I just record that value. Okay, and then you can eventually get okay, how many times it will visit each state, and then what is the stationary probability. So this is the long-term behavior, okay, over this transition matrix. So if you want to do using simulation, you can also calculate the long-term behavior of the Markov chain. Okay, up to here, is there any question? So if not, I will go to the next slide. It is the main one. In the next slide, I show that we can actually use matrix form, okay? The one that we discussed yesterday also, right? So we can use matrix form. Instead of one by one, instead of checking the state one by one, we want to get simultaneously all states. So using matrix form, you can calculate all simultaneously, all states. So now phi I here, okay, I can put that into a stochastic vector phi, okay, to show that this is the scalar and this is the vector. So I put both matrix vector, yeah. And then I define J as a vector of 1, 1, 1, 1, 1, 1, 1. Okay, of course, J transpose mean this row vector. So if you have a vector of J transpose multiplied by the stochastic vector, the sum, right, must be 1. Right? Why? Because the sum of stochastic vector must be all 1. Yeah? Remember, this represents probability, yeah? State probability, right? So the state probability in the whole network must be equal to 1. Earlier we already showed that. Yeah? So the transition probability Sj is a matrix, so it's basically conditional probability. So we have a matrix. Okay, this is the one that I just repeat here. Okay, now because the sum is 1, so then you can put, if you multiply S with J, J is a vector of 1, it will become J. This is linear algebra. Okay. So yeah, double stochastic matrix mean the difference is stochastic matrix and double stochastic matrix is this. If stochastic matrix, the sum of its row is 1. Okay. Double stochastic matrix means the sum of its row is 1, the sum of its column is also 1. Okay. So double. Okay. The sum of its column is also 1. So we don't use this anyway. So, and we already, this is just repeat a while ago, we have this, what is this? This is the total probability, this is the Markov chain formula, right? Basically, this is the Markov chain formula. This is the Markov chain formula, right? A while ago, that we use for difference equation. Okay, now based on that Markov chain formula, okay, I can calculate the same Markov chain formula in matrix form. Okay, how to calculate that? That is based on what is called Kolmogorov-Karpman equation. Yeah? That if you have a stochastic matrix S, and then you exponent with certain exponent, say S, small s, and T, okay, you can just multiply. Yeah? You just multiply them. If you multiply them, that's equal to the addition. Okay? So this equation is called Kolmogorov-Karpman formula. So based on this formula, we can derive the Markov chain formula, yeah, which is this equation. Yeah. This is exactly the same as earlier in scalar form. Okay, this is exactly the same as in the scalar form. So now using matrix form, this is much easier to compute. Okay, so based on this recursive formula, and you combine it with that Kolmogorov-Karpman equation, you have the Markov chain formula is not recursive but based on V0. So if you have a initial value, okay, and then you want to get the distribution of the phi at time n, what you will do, you just exponent s to the n, but this is the transpose. Okay, so using this formula very easy. Okay, so let's do it in, this is in MATLAB. I also created in Python. Okay, so all you need to do is to copy this in Python. Can you make it? So it's a simulation of the Markov chain given the S and V0. Okay. K is the number of steps that you want. So in here, in this example, I give S, and this is the V0. Okay. And then if you simulate this, okay, this is the result. Okay. So I plot this result, you will get something like this. So can you try to make this? Just copy and paste, yeah? or you just type. And look at the formula. This is just based on the, what is this? This is based on the recursive formula a while ago, right? Okay, try this. Yeah, you can open your Spider and type this. Yeah. Once you make this, you can change the stochastic matrix and the pi. Try to make this. So, and then you try to practice. Yeah? This is example of the run. Okay. Okay. So run this first so that I will discuss about the stationary distribution later. I want to get the long-term behavior. This is the long-term behavior, right? This is what we want to get in the long term. But you can get that if you print this result. Or you plot it. The same thing. Okay. Once you make it, can you share your screen? Shall I continue a little bit so that you can do something during lunch? Very cruel. But anyway, so uh, there is what is called limit distribution. Can you see my slide? Okay. So limit distribution means the long-term behavior. Okay. What is the distribution of phi k, okay, in the limit? Okay. So to compute that, that means the same as a difference equation. So okay, that means the equilibrium value. Okay, that is the same thing, right? Between regardless of the k, okay, you will have exactly the same value of distribution. Not we call this distribution instead of just one number, we have one factor. All right. So at equilibrium, okay, the phi, if you multiply by the S transpose, will exactly back to the S phi. Okay. So not always exists, but if exists, then this limit of distribution is the equilibrium. So this is called stationary distribution or equilibrium distribution. Okay. So this is how to compute. Okay. So this is how I derive to get the formula to compute. Okay. So and you get the S, you minus with the I is the identity matrix, and then you put 1, 1, 1, 1 at the bottom, okay, and then you use left general's inverse with this 0 and 1, or 0 with K, okay. So with that, you can calculate the stationary distribution. So during lunchtime, I hope you can also type this value. Okay, so then you can try if you get this stationary distribution of the S. So kappa you can put any value here. So 1 is the default. Okay, and this is how you get that formula that a while ago that I put here. Okay, so S minus S transpose minus I and then J, okay, and then we can solve that. Okay, linear algebra solve that, okay, and then you can get the phi. Okay, once you get the phi, you can also simulate what will happen. Supposed to be, if you are correct, okay, if you start with the stationary distribution, it will always straight line like this. Okay, and compare that with the if you start with any other value, okay, you will get initially moving, and then it will go to the same value of the stationary distribution. Okay, so try that first, and we can stop for a while for the lunch break. I hope after the lunch break you can get these two codes finished. Okay.
Okay, see you, sir.
Okay, you can update me with your project probably.
Okay, wait, give me a moment, sir.
Yes.
My internet's quite slow.
Hmm. How many Mbps the internet speed there?
Okay, so this is actually the title of my paper later. Analysis of queuing theory in hockey supermarket. So I have made the abstract and the introduction, the first chapter, and currently I'm in my second one. So the keywords would be multiple server model, queuing simulation, service time, inter-arrival time. The next, this is the second chapter, I believe, model description. Currently, I'm discussing about the present model and the data collection. Okay, so the methodology is qualitative. I'm doing a qualitative approach where we're doing a case study and an observation in real time. And data collection, all the data is obtained from 19 May 2022 on a Thursday in a random, it's random on starting from 11 a.m. until 1 p.m. So for 2 hours. And then I made a PMF table like the ones you made in on your tutorials.
Maybe the gradation is, so you get per 30 minutes, or maybe if you make it 5 minutes, we'll get better.
Okay, wait, I'll just show you. This is the data that I got.
Okay.
So how I collect it is I just when you register, then I time their
Okay, this is
service
very
time.
good.
Yes, until 1, I believe. I stopped at around like 1 plus. Then okay, for the arrival rate, I make it every 30 minutes.
Yeah.
So maybe
This
later.
one is the one that you need to change a little.
Okay.
So make it 5 minutes so that gradation, because it's only a lot of zeros, right? This is the problem.
Yes. Okay.
And then,
So I'll fix this. I tried to make the poison probability, but I still messed it up, so I didn't I'll figure it out later. And then this is the surface time. So the average surface time is 4 minutes and 44 seconds per customer.
very long.
And so it is 0.2 customers per minute.
Very long, yeah? One customer is 4 minutes?
Yes.
Oh,
because
service time, or this is inter-arrival between service?
This is service time.
One customer is 4 minutes. That's very long.
Yeah, the queue is full. So the thing is, in hockey, the no station on the what I remember on these days, there is no idle. So the worker is always working.
Wow.
So when this was queuing, this was already behind them.
Oh, really?
Yeah, so 4 minutes because I think it's quite long because at first they have calls to ask, do you have membership? What will you pay for? What will you use to pay? And then they move the stuff from the trolley and they shop in like quite big quantities. Some even took like 8 minutes because there's this credit card offer where if you use Citibank credit card with a minimum purchase of 600K, you would get like 100K cash back. So some will go into the supermarket for like several minutes to go back again to like add stuff so they will reach the minimum. Wow. That's why I think someone took a long time. Yeah, this one 8 minutes. I believe this is because of the credit card thing. They went back inside and the register wait for them. They get some stuff and go back out front.
Do you have any relation to the owner of the supermarket?
No.
No. So you cannot give feedback about this?
I don't know about that. Maybe hockey is quite open. They're quite open to like feedback and like those kind of things. So possibly.
Okay. Okay. Next.
Okay. Then this is the surface time, and then next is my to-do list. So since I already obtained the data, I just need to calculate the current model, calculate the the LDW, the expected total cost, and like efficiency. And then I will develop, I will input to other models to find is there any models that
Maybe you
will
can
fit?
try with MM1 but multiply by S.
Oh, here is MM1S in the current model. So it's MM1 multiplied by S.
Okay.
Yeah, okay. So I will try like MMS like 1Q.
Yeah, and then
Then
compare, right?
yes, of the optimization number of servers
Mm-hmm.
number, and then the queuing rule of thumb to predict
Right.
scenarios and the expected total cost for each model.
Okay.
We will find the most efficient, like the cost wise and like performance wise. And then I will just need to complete the paper, like tidy
Right.
it up,
Right.
and then we're
Right.
done.
Right. So I give you the here in the chat. Okay. So if you want to collaborate, for example, I can help, for example, in the paper writing. Yeah. So that will be the agreement. So I put
Okay, thank you, sir.
no,
By
that's
the way,
optional. That's optional.
okay. By the way, sir, I wanted to also like try the model where we calculate self checkout surface, but I don't think it's the one on your tutorial is as mm infinite, right? But I
Yeah.
don't think it works here. Yeah,
No,
in
that is
supermarket
just to
sales,
compare that what happened. Probably if you want to do is what happened if we improve the service, because 4 minutes is definitely too long, right?
yes.
So can you check in Google, for example, okay, other supermarket, yeah, anywhere in the world, usually how many minutes, okay, per customer, and then how many items that they sell in that. So
Okay.
it's on the literature. Okay.
Okay. I will try to find.
So once you know the literature value, then you can start to compare with this, right? So I guess 4 minutes is very long.
Yeah, it's quite long, and that's why the queue in hockey is. They have, I think, 10 not to 12 cash registers available, but on the daily they will open usually 6.
Wow. Okay. Okay. Good. Good. So far so good. So
Yes.
need to make it until finish in that case. Right. Okay. Good. How about you, Liffy? You want to present your progress?
Yes, sir.
Cool.
Okay, I have already like a bit, but I don't know whether it is applicable or not.
Okay. Try.
Okay. This one.
You can share your screen, Liffy. Yeah.
Okay. Yeah.
Okay.
Can you see my screen?
Yeah. Yeah.
Mm.
Okay. I'm curious. What is it about?
Actually, it's like a simple thing.
Okay.
So
So,
I picked assignment problem. And so the idea is Okay, so the idea is I have already like do a research like what kind of problem instead of like the transportation problem, like what I said before, and then I think this problem uh, must be must be applicable to this IFN.
Okay.
And then this is like, so for example, the S is like the source.
Okay.
Let's say the source is a company, and then we have for example 5 employees, so E1 until E5 there, and then like a project, so project 1 until project 5, and then the result is like the result, so it is the P, and then the what we want to do is we need to assign the employee to each project.
Oh, okay.
Yeah, but I'm confused whether I will use like the employee to a project or like a job to a machine. I still
Okay.
like that. And then the goal is to build an automated system where in the beginning of each month a company needs to do this matching. So imagine in a company they will not have only like 5 employee and 5 project. They will have more than that.
Okay.
Those numbers, and then and also this will be substantially more. So that's my idea, and I have already like tried to formulate the is it the
Okay. So, okay, very good. So, my ask question, can you show me again the diagram a while ago?
okay.
Yes. So, between E and P, is there any weight or any cost, for example, or any distance or a direction?
I'm planning to put like so for example if the E is the employee, right, and then
Okay.
the project, so I plan to like rate the employee based on, so for example let's say it is a software engineering company,
Mm-hmm.
then the employee must be uh, have several knowledge about the like Java, C, and
Okay,
X.
okay. So the connection, the connectivity here between E and P is the one that you input in that case. Is that what you want to say? Right? The one in red and
Yeah.
okay, okay. So this is the one that you input, right? So your input is basically a matrix A, adjacency matrix
Mm-hmm.
between E and P in here. Is that correct?
Yes.
So this is 0 and 1.
Yeah.
Is that the one?
Yeah.
So it's a matching problem. Okay. So now in that case, can you make an say Python program?
Mm-hmm.
Because your goal is to automate, right? Can you make a Python program given this matrix as an input? And then what is the output?
The output. The output. The I forgot.
So in that case, you also have another input that uh, each project, how many you can, how many you need, right? This is like
Yeah.
the supply and demand. This is like the demand problem. This is like the supply problem, right?
Mm-hmm.
So In that case, you have the sum in here and the sum of that. This is another vector that you want, right?
Okay.
This is another 2 input that you probably want to put in. Okay. So, and then the output is probably similar to this matching, but now you will, for example, if this is 1, it will become 1. If this is 1, can be 0, right?
Yeah.
Yeah. So this is assignment problem? Isn't that what you want? So this algorithm called Hungarian problem. Hungarian algorithm. Okay. And in fact, there is already module in Python that you can also use. I think the name is Mantes or something. You can just search in Google, okay, and then try to make this into your code. Is it possible?
I don't know. I'll try, sir.
Yeah, and then you will make a test. Okay. Okay, good. So that's what I hope you can make it. More weeks, you know. You need to hurry up. And then after that, don't forget to both of you, Joy and Leafy, don't forget to put the mathematical formulation of the optimization. Yeah.
Okay.
So you want to minimize or you want to maximize something, right?
Yeah. Okay.
Good. Okay, so yeah, you can do it.
Okay, sir.
Okay, very good. Okay.
For the output, I will need to make like one matrix again.
Yeah, the next time you present, that's everything already. Okay, so you can demo program
Okay.
also. You can demonstrate, and then
Okay, sir.
that this is correct, and demonstrate that this is optimum. So two things that you need to demonstrate. Number one is correctness. You need to prove. Number two is the optimization, that this is really optimum. Okay, test these two tests you need to pass. Okay.
Okay.
Very good. Okay, so let's go back to Markov chain. So, okay, share your screen about the Markov chain, the program that you make.
The one in Python.
Yeah.
Okay.
The simulation, right?
I tried the previous one, but I haven't tried the stationary distribution.
Ah, okay, that's fine.
But it works. We need to import. I forgot to import like NumPy and
NumPy.
pyplot. Yeah, but I already did it, so it now works.
Okay, can you show?
Okay.
Oh, okay. So, okay, let me get that value. Okay, can you make it 10 first? K is 10. Okay, and run it again. No, you just run.
Okay.
Okay. Oh, what happened?
Oh, no. Wait.
Okay, so can you record the value? 32, 3 point, what is that? To be, why the value is very big? Probability cannot be 9.5. Something is wrong. Ah, okay, your initial value is wrong.
Oh,
Yeah,
which one?
line 25.
Yeah.
So
Oh,
this one was 0.5.
okay.
Okay, now is okay. So get the last value. Can you get the last value? It is 0.3217 and then 0.4 and 0.41, and then that is the one that you put as the new pi. So you can copy that line 25 and then put it line 26. You copy line 20.
Like,
Okay, you can copy line 25 here, right? But okay, you copy that and then into the next line, correct? And then the value instead of 0.2, now you can put this value. So 321 something, right? You can copy that value. You can copy this and then yes, and then 0.4 something, right? Okay, and then the last one is 0.41. Okay, and then when you run this, what happens?
22.
Yeah, you just run the this one. Okay, so this is almost stationary. So so if you run until 100, k is 100. Okay, and now if you run until 100, the actual value is 0. Is that? So this is the one that you're supposed to copy. Oh, what happened? Why we don't have the value of? We're supposed to get this value, and then this value, and then this value. Anyway, so if you copy that value, so 36, 47, and then so you input that into the new pi here. Okay, this value 47 something. Yes. That is the third one, right? I think the third one, that one, yes. And then the second one is 47, 47, not 40, not 41. Okay, that one is.
Oh, yeah, wait. One.
Okay.
Oh, we are trying to get the last value, right?
The last value. Okay, and then the first one is around 30. Yeah, okay. So put that. So if we get that, okay, and then when you run, what happened? Oh,
Wow.
right. So this is actually the stationary distribution. Can you see that? So when you start with the initial value of stationary distribution, okay, then it's always stationary distribution. It will not change. Okay, but if you go out from that stationary distribution, from the equilibrium, then it will start to jump, yeah, move around, and then it will become stationary in the long run.
Okay.
Okay. So I hope you understand the meaning of limiting distribution and stationary distribution. Okay. Vivi, you want to show your work?
Okay. I have only that on the
Right. Okay. So this is the when you run. Okay. So you can go to tools. tools, preference, okay, graphics. Is there any graphics there? No graphics. Maybe IPython. Is it IPython?
Oh yeah.
Good graphic, yes. This one, the graphic backend, you can put. Okay, you can change that if you want.
So,
Automatic. Okay, and then click OK or apply. Okay, and then you can run again. So the error will disappear, I hope. Yeah. So yeah, you get the same result, right? So you can change this again, the last value. Okay, so in your case, 41, right? So this 41 point something, and then you copy into, before that, your file you copy first into the new value. Your file you copy first into new line. Okay. Yes, that one you can comment. Okay. And you can get the last value here. Yeah, your last value is not the same as Joy. So you can, this is the last, so this is the 0.5, you change that. Okay, and then go up a little bit. What is the, okay, 32, 32% this one, right? So the 0.2 you replace with that. And then the first one is 26. Okay. Right, when you run again, oh, did you run it?
yeah.
Oh, why still 0.2, 0.2, something is wrong, probably, I don't know. So, wait. Your code, let me check, yeah. 0.2, 0.8, 0.5, 0.5, 25, 65, 1. Oh, that's supposed to be correct. That's supposed to be correct. But I don't know why you cannot get the final distribution. Anyway, if you want, you can also get the same value instead of copying that. You can also use the code to calculate the limit distribution, yeah, the equilibrium, yeah, stationary distribution. So, yeah, thank you, thank you. So here, can I stop your screen sharing?
Yeah.
Okay, so if you use this, okay. So if you look at this, I have the additional code here. Okay, I have additional code here to calculate the stationary distribution. Okay, and then exactly the same as before. Okay, the difference is now the pi in here. I get it not from the input, but from this computation. Okay, from this computation, then you will get exactly a straight line. Yeah?
Oh, I got the straight line, sir.
Oh, you got a straight line?
Yeah, yeah.
Oh, okay. Can you show?
Oh, yeah. So actually, the
Oh
previous,
yes. You can.
yeah, we changed the graphic, right? And then I
Oh, okay.
back. Yeah, I try to change it back, and then yeah, I got it.
Ah, I see. I see.
Mhm.
I see. Okay, so you're supposed to get that straight line. So
Yeah.
again, the stationary distribution is to get that final value. Okay. So apparently, if only 10, you cannot get that. But if you get 100, okay, or more, probably you can get that stationary distribution. Okay, that's the point, okay, of uh, Markov chain. So is there any question about this? So far, okay, right?
Yeah, that's it.
Okay. So if you look at the slide, okay, so I mentioned there that actually the limit distribution, okay, what's the difference between limit distribution and the stationary distribution? Okay, limit distribution is the asymptotic distribution, right? Initially you move, and then eventually will become uh, yeah, it will become certain value, right? That's the called limit distribution. Yeah? The limit distribution is independent of initial state, right? Whatever initial state you put, it will always convert to that limit distribution. That only depends on your stochastic matrix, yeah? Your transition probability matrix. That one. Okay. Uh, when we said stationary distribution, is actually this is a special. Okay, stationary distribution is a special initial state distribution. Yeah? Okay, V0. Okay, so of course you get that from the limit distribution. Yeah, when you get say 100, yeah? K is equal 100. And then if you start from it, okay, the state distribution will remain the same, okay, as the initial state distribution. So in this case, stationary distribution is dependent on the initial state distribution. Can you see the difference? Yeah? One is independent, the other one is dependent. Yeah. Okay, so this is the a while ago. Yeah, the initial distribution. This one you will get a different value. Okay. Now I want you to change. I give you example this one. So suppose you have a 3 web page. Okay, so from A will go to A. From this is the link. You know the hyperlink, right? From A will go to A will go to B, A can go to C, B will go to A, B go to B, C to B, and then C to C. So from there you can calculate the Markov chain, right? So the question is, can you get like page rank? Can you get the rank of the web page? This is another example of application of Markov chain. Yeah. Okay. Now you have this, right? Can you calculate? Can you just change the S in your program?
Oh, in Python.
Yes, in your Python. In your Python, can you change it? And what is the stationary distribution? Yeah. The only thing you need to change is the S. Yeah? The transition probability matrix. Yeah? So say you have an initial state of anything, P1, P2, P3. It's up to you to decide. Okay. And if you calculate that, you will get this value. Is that correct or not? So the first one is 1/3. The fourth one is 4/9 and then 2/9. Is that correct? This is the limit distribution. Did you get it? How much do you get?
We only need to change the S, right?
You only change the S. The P.
Okay.
You want to share?
Okay, let me share my screen.
Oh. So what is the A, the first one? And you get the stationary distribution. The first one is 1/3, right? That is correct. And then the second one is supposed to be 4/9. Is that correct? 4/9 is 0.444.
Yes.
Yes.
Yes, it's correct.
Correct, yeah? And then the last one is 2/9. Is that correct? 2/9 is 0.222.
Yes.
Oh, yes.
Yes.
Is that so?
Yes.
Yes, very good. So now you get that limit distribution, okay? Now if you want to get the web page ranks, of course, in this case, you can see that B, right? B have contribution of 4, okay? A have contribution of 3, and then C have contribution of 2. So of course, B is larger than A, okay? And then all of the two of them is larger than C. So this is how Google make a rank of the website. This is called page rank. So now you can see the limit distribution have certain advantage. Yeah? If you know that, you know the probability, that means you also know how often it is going to be used. Yeah? Okay, so if you want, you can solve this. Okay. I will not give you homework on this matter. Okay, up to here, is there any question?
No, sir.
No?
Yes, all clear.
All clear, yeah? So let's go to the next slide, state classification. So I close this, and I will go to the state classification of Markov chain. Wow, this is very long. Okay, so now I will make a complicated things of the Markov chain, yeah, a little bit deeper than what you have learned so far. Yeah, so far you have learned about how to simulate, right, the Markov chain and how to compute the stationary distribution. Okay, so next meeting, in the beginning you will have a quiz. Yeah, so the quiz is simple, how to compute the is about Markov chain. Yeah, so all that you learned today, yeah? Including the periodicity, stationary distribution. Okay, just one or two problems in Moodle, so you can solve it in 5 minutes if you have the program. So you can make it first, prepare. Huh? Okay, so today we will discuss about classification. Okay. So network can be classified into two. Okay. One is called irreducible. Oh, it's double R here, supposed to be. Irreducible. Okay. So what's that mean? Irreducible means strongly connected. Strongly connected network is a network where you go, when you can go from one node to the other node, and then you can come back. Any other node. Okay. That is strongly connected. For example, road network is a strongly connected network, meaning that you can go from your home to any place, right? And then you can also go home, right? Okay, that is strongly connected network. Okay, and the other type of network is reducible. This is called reducible. Have two possibility. One is called weakly connected. Okay, the other one is unconnected. So if you have a network, say for example, this is your network, go here and then go there and then go back here. Okay, so you have three nodes. Okay, in this case, strongly connected, right? But if the two strongly connected network, okay, together form a network, that means these two are not connected, so it's become unconnected because from here you cannot go to the other part of the network, so unconnected. Yeah? There is also possibility of weakly connected network. What does that mean? Weakly connected network means you can go, okay, from one node, okay, to other place, but you cannot go back. Okay? So for example, you can go here, right? Go there. Okay? Okay, this is a network. You can go from A to B to C, but from C you cannot go back to A. All right? Yes, you can go back. For example, you add like this, so it can go back to B, but cannot go back to A. So this is called weakly connected network. Is it clear? Classification. Okay. Now, what do you think about this? Okay. Is this strongly connected or weakly connected? Yeah. So if you look at this, okay, the first one here is what? Weakly connected. Why? Because from here you can go to D, right? But you cannot go out from D. So D is basically a sink node. The same thing with A. A is a source node. Why? Because you can go out from A but cannot go back to A. Yeah? So this is a network with the sink and source is called weakly connected network. Okay? The same thing here. Okay? This is the source and this is the sink, right? Like the network of Leafy a while ago in your project, S and T, that is the source and the sink, right? That is weakly connected network. Okay? Now, the last network here is called strongly connected network. Okay? Why? Because from any node, you can go to any other node, and then you can go back. Right? Is it clear? Weakly connected, strongly connected?
Yes.
Yeah. So this is also weakly connected. Why? Because from this component 2, right, you can go to component 1, right? But from component 1, you cannot go to component 2. Okay, there is no source node or sink node, right? But there is source component here and sink component here. What is component? Component on itself is a strongly connected network. Okay? When we say component, that means a strongly connected network, meaning, look, from 5 you can go to 6 through here, right? And then from 7, you can go to 5. Okay, through. So from any node within one component, you can go to any other node within one component. But the whole network itself is weakly connected. Is it clear? The name component and weakly connected. Yeah. So it's not just sync node, can be source component or sync component also. So network with source node or sync node or source component or sync component are weakly connected, yeah, or unconnected. They are also weakly connected. Now, our interest, okay, one of the interests is strongly connected network. What is that? If there is a path from in the network from any node, okay, to any other node, okay. So in linear algebra, we call this matrix, adjacency matrix of this is called irreducible. Yeah? In graph theory, this is called strongly connected. Okay, so you can go somewhere, but there must be a way to go home. Clear? Okay, so Markov chain. Now come back to Markov chain. Yeah? Markov chain is irreducible if it has only one equivalent class. What is equivalent class? It's a strongly connected. Okay. Irreducible means there is a positive probability that the Markov chain will move from any state to any other state in finite number of steps. So in the other word, irreducible Markov chain has strongly connected network, okay, and then the state communicate to each other. What's the meaning of communicate? That means you can go to other state. Okay, you can go. There is a arrow. Yeah, there is a path. Okay, sequence of arrow from any node or state to any other node or state. Okay, so all state can be reached from any other state. That's the meaning of irreducible. Yeah. Again, yeah, irreducible the same as strongly connected. Okay, component is a strongly connected subnetwork. Okay, it's a subnetwork, but strongly connected. Okay, the same thing with when the term equivalent class. That means two states are in the same equivalent class if they communicate. What is the meaning of communicate? Can go from either state and then go back. Yeah. So remember, yeah, equivalent class the same as component, the same as strongly connected subnetwork. Okay, up to here, is there any question?
So far, so clear, sir.
Clear, yeah? Just the name. Okay. And the state represent as node in the network, right? And then the equivalent class or the component is just the subnetwork. Okay. Now, basin, there are two basin. One is called sink basin. The other one is source basin. Yeah. So the non-basin is called connector node. So how do you know it's a sink basin? Okay, it's a node where all links are in to that node. Yeah. Here, this is the example of sink basin. So only have in arrow. Okay, there is no out. The source basin is a node where all links are out of that node. So this is the source basin because, okay, all the nodes are out only. Yeah? The arrow is only out. So here is the connector node. Clear? Oh, example here. A is a source node, right? Because only have out arrow. Okay. C is a connector node. How about B? B is a sink node. Yeah? So sometimes we call it absorbing state. Yeah? Sink node is absorbing state. Okay, this is just the name classification of the node and the network. Okay, okay, so again, which one is weakly connected and which one is strongly connected? How about A? A is strongly connected, right? From any node, you can go to any other node. Yeah? This one is unconnected. So this is called unconnected is part of weakly connected. And here there are two components, right? CDE is a component, and then ABF is a component, right? Because from A you can go to B, okay? From B you can go to F, and from F you can go to A, right? So this is a component on itself, okay? But from D you can go to A but cannot go back to D. So in that case, this is weakly component, weakly connected network. Clear? Okay. So this is just the explanation. Now, next state classification is three things. Absorbing, you already know, okay, sync node. Okay. There is two more classification that you also need to know, what is called recurrent and transient. What is recurrent? Recurrent mean, okay, you can always come back here again. You don't know when, but it will come back. One day it will come back. Transients mean source. Okay? Once you go out, it is possible that you will never come back. Okay, that's the difficulty in Markov chain is actually about the jargon, yeah, the terminology. So I need to introduce this to you. Okay, so okay, now make it more formal. The state I is said to be recurrent, okay, if upon entering state I, the process will definitely return again. Okay, so that means that there is a probability, okay, if the state is recurrent, if only if the probability to return is infinite. Yeah? It always be able to return. How about absorbing state? Yeah? Absorbing state or the sync node, okay, is a special type of recurrent state because once you enter this, you will never be able to leave. Okay? And the same thing, if Markov chain is irreducible, right, then all state must be recurrent. Okay, test. Livy, what is recurrent again? What's the difference between recurrent and transient? What is recurrent? Recurrent mean, okay, so you can always go back. Okay? You can go in the loop and then come back here again. Okay? Transients mean it is possible when you go out, it will never be able to come back. Yeah? Transients mean source node or source component. Okay, so in irreducible or strongly connected, so that means you always can come back, right? That means the network is recurrent, the state are recurrent. Okay. Now, again, the state is called to be transient if upon entering the state, there is positive probability that the process never return to that state again. Okay, so formally we can say that the state I is transient if and only if there exists a state J different from I that is accessible from state I, but I is not accessible from J. So can go out, okay, with possibility, positive possibility, never be able to return. So you leave your parent and then after you married, you leave your parent and then never return. Then you are in the transient state. This is the example. Okay. So in weakly connected network, okay, if the state is not absorbing state, then it is called transient state. Yeah? So basically source component or the source node. Okay. Can you see this? Node 1, 2, and 3 are recurrent. Okay, when go out, can come back. Okay. There is a probability of 1 to come back. Here, 2 and 3 also can go out, can come back, recurrent. Yeah. Transient is 4, 5, and 6. Once you go out, yes, can come back, but there is possibility, say from node 6 here, if you go out, you can come back to here, right? But there is possibility that you go here and then go to the node 3, never come back. Okay, so can you distinguish between recurrent and transient in the network? Okay, and the last one is absorbing state. It's a sink state. Okay, how do you know? The stochastic matrix, the transition probability matrix on the diagonal is 1. Obviously, absorbing state is always aperiodic later. Yeah. So this is the example of absorbing. Where is the sink in this case? Where is the absorbing state? How do you know this is absorbing state? Yes? Can you say? Joy?
State 2 is the absorbing state.
Why?
Because it can never go out from state 2. It will just go, if it go out,
Right.
it comes back again to state 2.
Yeah, once you enter here, you can enter but cannot go out. Okay? And how do you know in this matter? You can see this probability here is 1. Yeah. In the diagonal, if the probability is 1, that is always absorbing state. Okay? Oh. If it is a component, okay, instead of a state, yeah, is a component, so we call this final class. What is final class? Is a component absorbing component. Okay? That from any other place can go there, but once there, it just look inside. Cannot leave that final class. Okay? Okay, so period we will discuss next meeting. Beginning of next meeting, we have a quiz. Okay? So please.
Okay, sir. Will the quiz be verbal or like in Moodle?
In Moodle, in Lentera.
Okay, okay. Okay, sir.
Just 5 minutes. So, okay. So be on time in that case, because it will be available only 5 minutes.
Okay, okay.
Okay. So see you next week. In that case.
Okay. Thank you, sir. See you next week.
Yeah.